Hello, welcome to our channel for probability and statistics. In this video, we will introduce the basic ideas of linear regression model. So linear regression is used to find some inherent linear relationship among the variables. So here you can see y equals beta 0 plus beta 1 multiplied with x. And this equation y equals beta 0 plus beta 1 x1 plus beta 2 times x2. So this one is only 1x and this one has 2x. So here this is a simple linear regression and this is a multiple linear regression. In all these two equations, y is the response or dependent variable, like house price and child weight, and x here are regressor or say independent variables, just like size of the house and age of child. And if we look at this figure in simple linear regression, we can see a straight line because this is linear equation. Why we call linear? Because beta 1, beta 0 are only a scalar. But x here can be x or x squared, no problem. So linear means the parameter is linear type. If x divided by beta 1, it's not linear for beta 1, right? So x times or x multiplied with beta 1, this is linear for the parameter. So for simple linear regression, we can show dependent variable and independent variable in a straight line in this figure. And beta 0 is the intercept, and beta 1 determines the line's position or the angle of this line. It's a coefficient. So we can see it's a deterministic relationship between two scientific variables. But why in real world, if the same child with same age, but they have different weight, and the same age or same size of the house have different price. So which means in the relationship between x and y, there are plus some not deterministic factors, right? So this is the concept of regression analysis, and we will use a statistical model to model this relationship. So the actual y is the opposite of the value equals beta 0 plus beta 1 times x, also plus a random term. So here, this random term epsilon is a random variable that is assumed to be distributed with mean 0 and variance sigma square. And variance sigma square is the same for odd value of x. So this is very important. We will show later in the figure. And this is called homogeneous variance assumption for linear regression model. Say single linear regression SLR model. If we look at this figure, based on previous beta 0 plus beta 1x, this is straight line, we also plot the real opposite of the value. Because this is straight line, you will never know. Nobody will tell you this is straight line. What's the beta 0 and beta 1? What we know is the opposite of the value for this point. This point can be stay here, can be stay here. For this x value, the point can be stay here, also can be stay here. But if we have many x value for the same x value, odd random term epsilon will follow some distribution which has the same variance, no matter which x value here is, right? So this is called a homogeneous random variable. So this is a very important assumption. If we look at this figure, x1 to x6, and this figure shows like a 3D figure in the two-dimensional space. So this is x and this is y. This is the deterministic relationship between x and mu y given x. So this line can be seen as the average value of a given x for the dependent variable, right? And this shape model the random term, the distribution of the random term epsilon. So that's why you can see you observe the value maybe here or maybe here, different value. But for different x, their distribution of this random variable are the same. So the epsilon has the same distribution for different x value. So in a regression model, x or the independent variable, this is deterministic. This is not a random variable. Just like a house age and child age. This is deterministic, not a random variable. And what we observed, the value like a house price, the weight of a child, this is random because this observed value has included a random term upon this deterministic relationship. And why we want to do analysis with the with the regression model? Because we want to know the parameter. And why we want to know the parameter? Because usually an analyst based on previous research results or from literature review, anyway from some no information and no theory, then build such a model, but never know the real beta 0 and beta 1. So we have to estimate these two parameters, but we never know. See, only what we know is the observed value for the y and the deterministic value of x, right? So from this value, we can estimate this regression line. We can estimate and using beta 0 for the estimation of b1 as estimation of the beta 0 and b0 estimation of for the beta 0 and b1 estimation of the beta 1, right? And this equation can be written as the y hat equals beta b0 plus b1 times x. So y hat is the predicted or fit the value from the estimated parameter. So beta 0 and beta 1 is estimated parameter. This is real value, right? And we show in this figure 1 is the theoretical value, but we never know this value for beta 0 and beta 1. And the other line, very close but not exactly the same. This line is y hat equals b0 plus b1x. So this is estimated or say fitted line from the given observation of these scatter plots. And we look at these two equations. So yi is the observed value. For the fitted line, b0 plus b1 xi, we have to add ei. So this is the regression fitted line's error term. And for the theoretical regression line, yi equals beta 0 plus beta 1 times xi plus epsilon I. So epsilon I is the difference between the observed value and the deterministic relationship theoretically, right? But we never know these two parameter. So in this figure you can see epsilon is opposite of the value minus mu yx equals beta 0 plus beta 1 times x. And error term ei is the difference between opposite of the value and the fitted value from estimation, right? So beta 0, b1, b0 and b1 here are the parameter estimated. So we can talk about the method of estimation. And the method of estimation widely used in regression model is the least square. So we should find b0 and b1, which are estimates of the beta 0 and beta 1, so that the sum of the squares of the residue is a minimum. So the estimation process is optimization problem. So we have to make a minimum of this error term in between the fitted line and the opposite of the value. And the residual sum of squares is often called the sum of squares of the errors about the regression line and is denoted by SSE. If you look at this figure again, this error term, EI, take sum, then put together this summation of these error terms square called SSE. So if we make this sum of the squares minimum, then we can say this line will be best fit with the theoretical line. So mathematically, if we want to get the SSE, we can just write this form. The difference between y is opposite of the value and the fitted value. Then take a square, then sigma for all observations. Then SSE make differentiation of SSE with respect to B0 and B1, because we want to estimate these two parameters. So we make differentiation, then this is the result of the differentiation, and then we set these two partial derivatives equal to 0 and make some manipulation. Then we can get sigma yi equals this form and sigma xi yi equals this form. Then from these two we can get the parameter b1 and b0. Actually b1 is the division between the cross products between x and y and divided by the second moments of x with the mean of x. And beta 0 is a very simple form. So next we show an example using linear regression module. So this is a table of some data. The y value here and x value here. So y is the oxygen demand reduction and x is the solids reduction. So we estimate the regression line for pollution data in this table. So the solution is quite easy. We just fill all data and get several results for xi sigma, yi sigma, and xi yi and xi square. I will take a sigma. Then we just fill this number in b1 and b0's formula. So we can get these two parameters. So which means y hat or the fitted line, this is the results for the fitted line. I'll say y hat equals beta b0 plus b1x here. And from this fitted line, we can also get 1-point estimation or prediction. Say, for example, 31% reduction level, we can get 31 reduction in the chemical oxygen. This is Y hat when the X, or say the reduction in the solid is 30%. So next videos we will go into more details and assumptions and more advanced topics around linear regression model. Thanks for watching.